And it's always fun to watch the next generation come up and see what kind of cool stuff they're doing and understand, how the world is different from where I was at and, what's important and what's not and how we're going to move the ball forward. So today I have a full panel of people who've done exciting things themselves. Some have more or less gray hair. I'm looking at you. And they each have their own exciting story to say, so I'll let them do it.
Okay, so I'm Martin. I didn't know what a compiler was until I was 23. I thought it was a little computer that would sort of transform my programs and push it to a big computer, because the TAs always said it didn't pass the compiler, so I thought it was a machine. Once I found out what it was, I was hooked, and I wrote quite a bunch of them. And nowadays, I'm mostly about disrupting the Scala language.
All right. I'm Marius Eriksson. I guess I also have a formative story about compilers, which is the advanced compilers class in school was kind of what got me hooked into doing all sorts of low-level computing and things. It's a very exciting field, I think. Most recently, I've been working at a company called Grell, where we apply really large-scale data processing and machine learning to detect cancer at a very early stage.
Yeah, my name is Runar. I'm one of the authors of the Red Book, Functional Programming in Scala, which I trust you've all read, right? I've done all the exercises too. I'm also a co-founder of a company called Unison Computing. We're making a new programming language, which is awesome. And that's me.
So I'm Julie, and I got to know Alexi when I showed up at a Scala.js hackathon a few years ago, and for some reason he keeps inviting me back to these events. But lately I've been in the machine learning infrastructure space, which has nothing to do with Scala.
Hey, I'm Brian. It's great to be on such an august panel. I am not a programming languages person. I'm not a PL person. I'm a systems person, and I'm slightly nervous that this is all a trap, and I am going to be held hostage and ransomed back to the systems community in exchange for God knows what. So if I'm eyeing the exits, that's why. So my whole career has been in operating systems development, a lot of OS kernel development, a lot of C, a lot of assembly, and recently, and maybe this probably is why I'm here, I have fallen in love with Rust.
It's a geek conference when you're in love with the new program. Okay, I'm gonna get started here, and I'm gonna pick on people in turn, and then we'll just kind of let the conversation flow after that. And so for Martin here, I guess sort of the first comment or question is basically, Scala reminds me of sort of like the C++ of Java. It's got every possible bell and whistle on the planet, and if you use them all, you can't even read what you wrote. So you have something to say about that?
Well, thank you for that, Cliff. Well, if you look at the language size, it's actually not true. Scala is about half the size of Java. You would be surprised. But if you count language features,
Java didn't used to be so big.
So just to give you one example, Java has two language features for conditionals. It has an if then else and a conditional expression. Scala is only one, and there are many other examples of that. So actually, the grammar of Scala is significantly smaller than the grammar of Java or a lot of other industrial languages. That's, I would believe, it's academic heritage. Academics like to do small languages and essentially not to put a lot of bells and whistles in the language. What might look like bells and whistles are that Scala is very orthogonal, so you can combine things in infinitely many ways. And yes, that has been misused, and we are looking at ways to reduce that, both by essentially teaching people not to overuse, let's say, symbolic operators and stuff like that, and by putting more restrictions in the language and thinking of implicit conversions.
Are there any features you're wishing you hadn't put in that maybe you're thinking of taking out?
Yeah, we're taking out quite a few. So the one thing we're going to take out is XML literals, which were all the rage when Scala got invented. You know who made me do that? Phil Wadler made me do that. So he said,
Phil's not here, I didn't do.
No, but he said you have to put XML literals in the language. XML is the future, so everybody will, you can just cut and paste web pages into your program and it's cool. So that's why we did it. So we're going to take them out again. We're going to take out quite a few other things, procedure syntax. We're going to restrict implicit conversions, existential types. So the new language will be slimmer and meaner than we don't ever before.
Cool.
No.
Yeah. Once burned, twice shy. So Marius, I even forgot your intro. What were you talking about?
Large-scale data processing, cancer, early detection. Previously, I'm more known for RPC systems and microservices. Things like this.
Oh, microservices. So microservices always struck me as a thing for people who didn't know how to program. It's like programming for script kiddies or something. What is it? How is it useful over just writing your code?
Well, it is just code. It's a different way of packaging it, right? So I mean, I do agree that most of the time when people do employ microservices is not necessarily for a good reason, and they'd be better off just writing more monoliths instead. But it is a very useful tool for companies like large companies like Twitter and Google and many others that are operating at large scales to sort of produce a system where individual teams have much more autonomy than they otherwise might. So an old colleague of mine, Jake Donham, actually had this recent talk where he sort of made the argument that the main trade-offs that microservices presents is to give sort of a new point in this set of trade-offs between autonomy and leverage, right? And what is meant by that, and I found this to be a very nice distillation, I think, of why we pursue microservice architectures in the first place. And what effectively meant by that is that as a product scales and as systems scale in terms of developers, at some point, it becomes kind of intractable to even make small changes to large code bases. And so you have to either invest very, very heavily in development infrastructure, or perhaps fragment your large monoliths up into smaller pieces that do kind of retain tractability of doing engineering and deployment and autonomy. On the other hand, you lose a lot of leverage, which is the sort of everything from the fact that you're now introducing these network boundaries where none existed before, right, which is a huge source of complexity, to the fact that it's harder to share code across them. You have to coordinate now and deal with serialization concerns, and you're introducing a lot of complexity that didn't exist before, right? But you're able to make independent progress in these sort of individual islands. And so I think the interesting thing about microservices is that as we sort of initially split things out, we gained back all that autonomy and was able to make progress, and have sort of slowly been recovering a lot of the leverage since by introducing new abstractions, new libraries, new ways of sort of thinking about how to deploy and operate the systems.
Sounds like a better way to scale out people.
That's exactly right. Yeah, I don't think you should even think about microservices until you have a people problem.
Cool. Okay. So Rainier, is that right? How do I say it? Runar? Yeah. Okay. So I have a functional programming question for you.
Okay.
Why are they so slow?
That's a very thoughtful question, Clint. So functional programming is slow in Scala. But I mean, it depends on how you do things. I think that you have to be thoughtful about how you do things, how you implement things purely functionally. And yeah,
So you have to pay attention to like real world physical concerns while doing functional programming.
Yeah, you do. Like you have to pay attention to whether you're going to run out of stack or whether you're going to generate a lot of garbage if you're running on the JVM, things like that. Or you might choose your language very carefully. Like you might want to choose a language like Haskell or Rust if you're going to be heavily into functional programming. And you want to be fast, but you don't always want to be fast. So sometimes that's not what you are optimizing for. Sometimes what you're optimizing for is compositionality and comprehensibility rather than like running really fast.
Are you saying that if you come back to a project in 3 months, you want to be able to understand it without 3 weeks of untangling the code?
That's exactly right, Julie. I mean, because spending 3 months or 3 weeks or whatever on understanding, your C++ program or whatever is not fast.
I will add that you can write unreadable code in any language.
That's true.
Okay, so for Julie, you've been doing some ML stuff recently. Is that what I got? Okay. God, where to go with this one? There's so many directions. So ML is currently touted as the savior of the planet, or maybe the killer of all the robots are going to take us all over or something. Where is the media hype meet reality actually?
I think they're in parallel dimensions, to be honest.
Sort of unrelated tracks going off in space in different ways.
And let me give you an example. I'm gonna pick on either Alexi or whoever put together the blog. I did an interview for the Scale by the Bay blog, and I said something about, before I learned anything about machine learning, it seemed like magic. And so I wanted to kind of unpack that. And the headline was, "Machine learning is magic," was out of that blog post. And so even at a tech conference, it's easy to get carried away at like, it's going to be this magic bullet that solves problems. No, it solves very specific subset of problems where it's really hard to write a program for. And that's more or less the extent of the state of the art.
So it solves a very narrow domain. Would you say it looks something like maybe a better microscope to looking at your data, a better way to understand and look at some piles of data?
I mean, I would say it's better at looking at predictions that you wouldn't otherwise be able to make based on data that you haven't yet seen. So it's not that narrow, right? I don't want to sort of undersell it, but it helps you understand sort of latent properties of some sort of domain that you might not otherwise understand. So, I mean, at the end of the day, it's more or less applied math.
All right, thanks. Okay, we got Brian down at the end here, and you've been doing stuff in Rust. And I guess the easy question here is, when does Rust get a GC?
The day before I stop using it. Rust has made it actually a very interesting bargain where you get the power of, I mean, I think even the distinction between like a functional language and an imperative language, I mean, I think all these things are drifting together. But Rust, you get a lot of the power of a functional language, you get a lot of the power of a modern language. But you actually do that in a way that is as memory explicit as C. And actually what I found, the thing that's been really interesting for me, is that it actually outperforms C. That's been really surprising, and in part because you can actually, because you can compose things so much more easily than you can in C, you can actually get super high-performing data structures in the kind of core library, but you can then you can use them really easily. And so what we end up with, or what I've ended up with, is kind of like knuckleheaded Rust outperforming my hand-optimized C, which is a very crushing experience, by the way. To think like I really spent a lot of time on the C, and this Rust that I just kind of threw together is outperforming it for the same task. But the reason for that is because it's actually you're able to build much more sophisticated data structure. So Rust, I mean, it is a bargain that you have to, that you're making, and that you are having to think a lot more about it, and it uses affine types, which is not something you've seen in a lot of other languages. I mean, I think there are other languages. I made the mistake of saying that Rust was the first programming language to do this, and of course, which is almost never the case, right? Anytime you like something in a programming language and you want to talk about its novelty, someone has to come out of the woodwork, probably sporting more gray hair than you have, telling you that no, Simula did this and Operon did this, and it's like, all right, Jesus Christ. No. But affine types, I feel like I know a lot of programming languages, and I do feel like the ownership model. I'm like, okay, I know I'm going to regret saying this, but I haven't actually seen this in other programming languages. I'm not a PL person, but I haven't seen it. And immediately someone's like, no, Clean did this years ago. Like, what the hell is Clean? And I'm often like, it's a terrible name for a programming language, but Clean is, and I'm sorry, I'm sure I'm mortally offending everybody. And so, all right, fine, Clean did this, but there are very few programming languages that have done this, and it's a really interesting bargain that has made it's really intriguing, and it has allowed actually systems programmers to now get a really powerful modern language.
why can't I have a cake and eat it too? Why no GC? Why
Well,
not both?
I just think that if you need GC, like this is not the right language, honestly. I mean, I really do think that. I mean, because I think that I mean, Renard's exactly right, that you don't always want a high-performing artifact is not the primary goal, always. And you don't always want the bargain that Rust has. The bargain that Rust is going to make is like, look, you are going to think a lot about this artifact up front, more than you would for other programming languages. In return, I'm going to give you an artifact that is higher performing and more durable. That's not necessarily a bargain you want to always make. You want to do speculative software engineering. You want to be able to kind of quickly concept things on the fly. And so you don't always want that. And if what you need is garbage collection, there are lots of great languages that are going to allow you to get that.
I want both. I do big data with all kind of complicated infrastructure around it, and I do core inner loops that run over terabytes, and I want those core inner loops to run fast. So I actually want both.
Well, so I think the thing about Rust, though, is you can't have both. I mean, with Rust, you effectively are doing both because you were doing mental GC as you were writing your code.
It's the other way around. I let the GC pick up all the crappy code that I don't want to think about, but in the core inner loops, I do the hand-generated affine function thinking about what the hell is an object and when is it live and when its duration is, because that's where it matters for performance. It doesn't matter everywhere, so I don't want it everywhere.
So what I've found is that that in languages that are GC'd, that when you have this idea that like part of my software I'm going to really care about, and the other part of the software like I just don't care about, and like we can just like poop all over it. The poopy software always ends up overwhelming what was putatively the high performing software, and a stupid mistake somewhere in the software that you're just kind of like blathering out ends up actually holding that object reference that actually causes your heap to explode, or that's the code that actually does end up being in the loop when it wasn't intended to be, and you end up spending a lot of time debugging that. And so Rust, and again, the position that you don't have to agree with Rust's position, but you kind of have to admire it for it, how unilateral it is. Rust is like, I'm just not going to let you write crappy code ever. Like, I'm going to be up in your grill, like, every time you want to do something, I'm going to make you write it correctly, or as correctly as I, the compiler, know how to enforce. But it's to a remarkable degree. And there are a number of kinds of software defects that are very hard to actually make in Rust. I mean, it is so, I mean, around signed extension and arithmetic overflow, for example. I mean, it's ridiculous how up in your grill it is.
Okay, I think we got that you're passionate about Rust. So I'm gonna try to rotate the panel to a different topic and maybe a different speaker, and ask the questions about, well, it's thoughtful engineering, and in 30 seconds or less, what does thoughtful engineering mean to you? And we'll just roll down the list again here.
I think it's being able to think in many different abstraction layers. At the same time, essentially write your software to a high level of abstraction, to a high level of correctness, and know what it maps to when you have to, and essentially not mix up the two abstraction layers. I think that's a key element of thoughtful software engineering for me.
It's hard to disagree with that. I mean, I think to sort of add on to that, there's a certain art to knowing when you should erect sort of an abstraction and introduce one, and when you should tear it down. It seems like actually most sort of software innovation is either one of those two things. You're either kind of tearing down abstractions that exist and finding a way to simplify things, or introducing an abstraction that gives you kind of more leverage on top of it. And to add to that, I'd also say that one thing that I sort of associate with thoughtful software engineering is to sweat a lot of the small stuff because it adds up, right? So we think a lot about like sort of high-minded architecture stuff, but really just like being very, very persistent about sort of sweating out the small details, getting everything correct, and being persistent about that is something that pays off in heaps and spades usually.
Yeah, to me, thoughtful software engineering means sort of taking a long-term perspective, or taking sort of a higher level view of things. Like thinking about what are your goals really? Like are the short-term goals that of the business immediately, are those really the goals? I question that. And then think about like the total cost of ownership of the software that we're building. Because I think that as software engineers, we're actually really bad at this, at estimating this sort of total cost of ownership. And so making sure that at the end of the day, we're creating an artifact that is an asset rather than a technical debt in our code base.
I think thoughtful software engineering is caring about the person that has to deal with your code when you're gone. Thinking about how can you make that code better. My first time as an engineer at Netflix was the first time that I had to do code reviews, and I had a very thoughtful panel of code reviewers, and so what it taught me to do was think about what is that most thoughtful person going to say about my PR before I submit it, so that I don't have to hear all of their comments. So at the end of the day, if you leave a company and you encounter one of your former colleagues and they're not face palming over all of the mess you left behind, that's probably a good sign that you've been thoughtful.
Yeah, I would echo exactly what Julie said, but I'd take it up to another level of magnitude, because software, I think we kind of lose track of this in how easy it is to create software and destroy it, but software is a mathematical machine. And software, unlike everything else we build, unlike everything else we engineer, software can survive in perpetuity. Was Euclid writing software when he wrote his GCD algorithm? If your answer is no, you're going to get wrapped around the axle on some really nasty paradoxes. Your answer is going to have to be yes, that Euclid was writing software, even though he was writing it several thousand years before the computer. All of us in this room will probably write software that at some point in our lives that will survive us. And perhaps survive us by millennia. We may be living in the ancient Athens of software right now. And so I think that it sounds heady and ridiculous, but you look at how much software we are still running from the big bang of software in the early 70s, and it's entirely reasonable to think that it will survive in perpetuity. So thoughtful software engineering is thinking about not just the person that comes next, but actually the generation that comes next, and designing software for timeless correctness.
I will add that I've had software I wrote 30 years ago come back to me after 30 years and say, hey, we're still using this. Oh. kind of an eye-opener there. Yeah. So I didn't hear anyone say tech debt elimination. I didn't hear anyone say running a continuous integration process. I didn't hear anyone say JUnit testing. I didn't hear anyone say, well, there were some code review comments that happened, but no one said, hey, code reviews. So is there something about thoughtful software engineering that includes the process by which we make code? Anyone want to take that up? The process by which we write bugs.
I guess maybe when it comes to process, maybe my overall theme was that sort of thoughtful software engineering involves people, so not sort of over-rotating on the actual tech or the actual code you write, but actually how do people interface with that software. And I think it includes considering where it's going to go down the line, which means you need to have a process. So absolutely thinking in terms of, we're getting something into, a production environment. Let's say it has to have a life. What are we going to do when there's, failures? How are the teams interacting around this software? So that's absolutely included.
So software is a team sport.
Yes.
You mentioned the long-term. You mentioned the testing, and I think it's part of this sort of long-term perspective that tests communicate to people far in the future, or maybe in the near future, maybe a millennia in the future, what it means for your software to function correctly. Right?
So testing as documentation of expected behavior as a contract.
Exactly.
Actually, I totally agree with that.
Actually, I'll also add to the sort of theme around code reviews. I feel like code reviews serve a number of different purposes. So one is obviously to kind of vet the correctness of the code and to make sure that it fits in with the other code that you might have around it. But I think it's also a huge vector for education, both ways, right? So it's a great way to sort of indoctrinate people into a particular project and teach them about the abstractions that exist and how things are done, what the local idioms are, and things like this. And I find this to actually be one of the most effective ways to sort of introduce people to both the local vernacular as well as just sort of general engineering practices. And so, you know, and the theme of working with people, I think this is one of the sort of greatly underappreciated aspects of code review that is used, I think, quite extensively in the industry.
Has anyone here worked on sort of larger projects where code reviews were not the norm, as opposed to were the norm? So I certainly predated all like coding standards of every possible kind, and code reviews were not the norm. And the jump to code reviews was a hard one, but definitely a highly valuable one.
When was that jump in terms of like, because I mean, when I came into, I worked in source kernel development, and I came in the mid-90s, and code review was already very well indoctrinated there.
First time I saw it was probably mid-90s, yeah. But it was not everywhere, because I left there and moved on and didn't have code reviews again for a while, and then did and did not, and then finally did sort of regularly after early 2000s. But it was really, there was a 5 to 10 year window where some companies did it and some did not.
It's one of the things I miss about those days of code review is that they were all printed out. And you would, I know now I sound like a
You can still do that, you know.
Printing out, there's something about actually printing out the diffs, sitting in a conference room, and actually going through it with, for me at the time, going through it with more senior engineers, to your point about education. I also think that what I found is that the most important code reviewer is yourself. You have the best context on the code you wrote, and just to your point about reviewing your own code before it is actually reviewed by others, it's amazing what you can find when you actually look at the code you wrote.
I find it's very helpful to talk to another person about my code without them actually having to like look at it really, because the act of having another person makes me quit skipping over all the little steps I skip in my head, and I do the actual logical thinking process, and then all the holes in my thinking come out, and like, oh yeah.
Can I ask you about a question about block comments? Because I believe that like block comments are free from a compiler perspective, so we should err on the side of writing novels as we are explaining our code.
I totally. But you should go first.
I'll just say that there's when it is resolving uncertainty, when it's providing clarity, yes. There's wrong ways to do it. I worked with an engineer who would literally copy and paste emails threads into the comments. And that just didn't help at all.
I have so many follow-up questions.
Yeah, so I personally enjoy people who write in bigger chunks to do a bigger problem, and then they have to comment in a bigger chunk to describe, hey, this next couple stanzas are going to solve blah, blah, blah. And so there's a high-level overview. Once they understand the high-level overview, for me, having sort of a line-by-line comment's like less helpful. I don't need the long variable names, and I want to understand the big picture, and then everything else like fits in.
Yeah, this is what we used to call these big theory statements. This is if you knew Jeff Bonwick at Sun, Bonwick was famous for these big theory statements that would explain the entire subsystem, and then you didn't need the line-by-line comments.
Does anyone want to jump in on coding styles before I rant?
Consistency, that's my biggest thing. Just don't have 5 styles.
I think pretty much if you make a language from 2000 or even 2016 and on, it should have an auto formatter, and that should be the only thing that matters.
For me, the most important part there is really naming. So basically, name every intermediate result that you have. And I believe in particular in Scala, that's a lot abused, that people write like expressions that go over 10, 20 lines because they can just compose a map with a flat map and so on. It's hard work to find good names, but it pays, and I think one should insist on that. And that's one thing with all its restrictions that Python sort of got right. So Python didn't want to give you lambdas because they would lead to that. So they said, well, you have to essentially pass a named function, and that forces you to give a name to that intermediate result. I'm not advocating that we should go back to that, and I like lambdas where they are, but I wish people would use more names, because that's really underused right now.
I have a... Okay,
So one thing on style.
Okay. Yeah.
Can we But I totally agree. Consistency style, have a tool that enforces it. But for the love of God, can we stop in the 80th column, please?
So I've been down, I predate all coding styles. I've worked in a lot of teams where no one had even heard of a coding style, and then when they did, and they believed it, and they loved it, and they hated it. And what I found is the number one rule about coding styles is that I've never seen a coding style make a project or save a company, but I have totally seen coding style wars break teams apart and cause them to be dysfunctional. And so they start to hate on each other, and then it's not safe to talk what's really important, because your comments are wrong, or your camel case is not underscores, or you're past the 80th column. Sorry, I do that. It's important that people agree that it's okay to disagree. And what looks like wonderful code to me look like horribles to you, but maybe vice versa, and not one coding style rules them all. And get used to reading somebody else's code. And then when it comes time to go hack in their code, oh, there's an ownership of code notion there, honor their style. But if you're going to replace it, it's time to do tech debt replacement, yanking, rip and replace kind of things. It's your code now, you're going to own it. So you should write it in this style that lets you write it most efficiently as possible. And then for somebody else, they'll have to take a little bit of work to understand that code. And I've lived by that mantra for quite a long time now, and it ultimately, for me, it has paid off in all the teams I've worked with.
I don't know, I think Richard from that show Silicon Valley would disagree with you. He broke up with his girlfriend over tabs versus spaces.
I will say tabs are the work of the devil.
So I think as
PI is like horrible too.
Now I'm in the wrong room. This seems totally uncalled for. I do think I've experimented with all this stuff, and we went to what we call the states' rights model, where exactly what you were describing, where you kind of have a consistent style within a file. The civil war over white space didn't actually end, though. That doesn't actually, and it all became very passive aggressive. One person making hard tabs appear as poop emojis in their own editor.
The fix for that is to make it public and announce that that's what it is, and we can agree to disagree. Well, you don't let the thing fester.
I find that proxy wars over white space are usually like a marriage where you're arguing over the toothpaste. It's usually a symptom of something deeper.
And toilet paper this way or this way.
Absolutely. And if there is an ardent disagreement over that, there's probably something deeper going on. And I think you've got to address that deeper fracture.
Does anyone want to stand up and volunteer that Go's doing the right thing with their A1 format to rule them all? I heard a lot of applause. Somebody in the audience will definitely stand up and do that.
I think it's the right thing. I'll vouch for that.
So there is one right coding style, and they got it right, and that's it.
There is one right code formatting, which is not necessarily the same as coding style, which cannot be enforced really. But yes, it resolves all these arguments. At Grail we work primarily in Go. There's zero arguments about anything to do with formatting because there is just one.
So why doesn't the compiler just enforce it as a style, as a part of the compiler language spec?
I mean, I guess it could, but why
You'd be okay with that?
It's unnecessary.
Because I have a tool that forces it for me, which is not the compiler, but it does the compiler's job.
I'll point out that in Unison, the language I'm building, once you submit your source file to the code base, it gets erased, and so formatting is enforced. You can retrieve your code base in the enforced formatting, but you can never get back the formatting that you wrote it in.
I've never met a formatter that didn't screw up at least one of my block comments.
So I'll add to that a little bit too. I think one interesting side effect. I don't know which direction of causality this actually happened, but because Go has very strict requirements around its code format that is always correct and so on and so forth, that has created a very good sort of ecosystem of other tooling that can ride off of that. And as a result, it's very, very simple to write tooling over Go source code, right? Because it's been kind of a first-class design principle or constraint. And you actually see that in a lot of very rich tools for Go that are also very simple.
I guess as a long-time compiler guy, I'd say that's sort of the easiest piece to take advantage of, and the actual formatting didn't really matter to having a rich code base, but a lot of good engineers from Google piling in do matter.
Let me rephrase that a little bit. So because Go has a pretty printer that has a canonical representation and retains formatting of comments and everything else.
Including if they're in the middle of stuff.
All those details are already sweated, and it's a part of the standard Go library. Building tools that does source code transformation is just extremely simple and standard, and it always outputs the same thing, goes to the same code path.
I'll still claim it's nothing to do with the formatting, but you can get a toolkit that does that well.
Well, one thing that does help, though, is that Go's grammar is unambiguous. There are no shift-reduce conflicts, things like this, right? And so there aren't, everything is very unambiguous and simple, right? So I guess that's where the language design aspect of this comes in.
And language design is a hard thing. There's no doubt about that. So on the end here, I saw you like dancing up and down. Were you about to say something?
No, I was probably still reflecting on your comments on VI. I think it was just a fight or flight reaction, delayed fight or flight reaction I'm over here.
Emacs, join us.
Okay.
All right, the floor is open. Somebody say something, obnoxious.
Well, I do think one of the dangers, if you're asking about Go and the kind of mandated formatting, I think one of the danger actually in Go is a kind of tradition of intellectual autocracy that has grown into the language.
It's not very old. How did that happen?
Well, it's older than you think, and there are a lot of decisions that are kind of fickle, and the way those decisions are made they're not very broad-based decisions, and I think that and there's all sorts of strange idiosyncrasies.
Just the Java GCP process.
Yeah, right.
In the background. Like,
Clearly
oh my
an
God,
opposite
don't go
extreme.
there.
Right, clearly an opposite extreme. But I do think one of the dangers is that, the number of people that told me that Go should never have generics and would repeat the liturgy about why generics are absolutely inappropriate for Go, and then are now have thrown that liturgy out and have replaced it with new liturgy about how generics are coming to Go. I think that is actually a problem, and I think the formatting much more reflects that than it does.
The flip-flop from on high or the flip-flop from the masses?
Flip-flop very much on high. Right. I mean, the Pope has changed his position on generics, so now it's like now we can have generics.
Abortion's okay.
Right. I think it's great that the Pope changed his mind. I mean, that's nice. But it's great that generics are coming to Go. But I think
what's next? Gay marriage?
And there are analogs for that in Go, right? I mean, I think that that would be the death of Sego. I think would be the actual. But I think that I do think is corrosive to that particular community. I do contrast it to Rust, and I think that one of the things I think is interesting about Rust is that you've got a very broad-based community making very directed decisions, and they are doing it because they are unified by their values. And they tend to look at every programming language that's ever done anything when they want to do something and try to figure out all these lessons from these other languages. And I think part of the frustration that I personally have with Go is sometimes it feels like it's not looking at languages that came before it.
So ask again, when does Rust get GC?
Well, I think, but I think that Rust's principles are around being fast. It's a blazingly fast modern language.
I had 90% of my code. I don't care if it's fast. It's good enough.
Well, then you can create an RFC for that. I mean, honestly, if you wanted to do that, you would create an RFC for that, and you'd start that conversation with the community.
It's much more effective standing on stage and whine.
Fair enough.
So actually, this observation is I think highlights a sort of interesting aspects also related to thoughtful software engineering, which is there's often this sort of trade-off that exists between what you call intellectual autocracy, very haughty,
very autocratic. Okay.
Yeah.
There you go. I see what you did there.
And sort of this more broad-based decision making and so on. I would say one aspect that I think Go has handled very well is to really focus on simplicity. Right, and I think that's something that would really be difficult to do, and in a different model, right, of authorship and design decisions and things like this, because it's always so tempting to add features here and there and sort of cater to all these cases that may or may not be so important. So yes, you definitely do. Sorry. You definitely do up in a different place, and I'm not necessarily making a judgment about what's better or worse. But that is a sort of interesting part of the design spectrum, and sort of it's interesting to see how different designs end up just sort of based on the social and technical hierarchy of how that artifact is created.
Okay, I think we're running low on time. Does anyone want to add any last minute? Here's what I think is wrong in the world, and I'll add to begin with, to open the door. No modern programming language talks about time. You cannot reason about the speed of execution of your code with a compiler to back you up and support you. You don't get an SLA on any function, however trivial it is. Is it running 1 nanosecond, 1 millisecond, 1 year? You don't know, and the compiler is not going to help you at all. So the act of writing code that has performance guarantees becomes a freaking trial and error, becomes a try and test and load balance and optimize and just hope that it's actually going to give me 5 nines when I need it or not, and you just don't know. And it's high time to get a programming language that mentions time as part of a first class.
Actually, like Oberon did that in the 80s.
It looks actually that with modern computer hardware, this is ever more difficult, because it's actually the hardware already that becomes unpredictable with caching and multi-threading and things like that. So I don't really see how a compiler could give you hard-clad guarantees without going to a much simpler hardware model.
How about an SLA where I get like a bell curve with statistics? I'd even take that.
Okay.
And do side channel vulnerabilities make that more difficult to offer the programmer? I mean, because I think that 2018 has been a very difficult year. Our annus horribilis in terms of writing secure software, and now it's like a high resolution time is suddenly a security vulnerability.
It turns out, statistically speaking, you don't need a very high resolution timer for Spectre meltdown to work. You can use a very low resolution timer and still have them be reliable. They started with high res, but once you apply some stats, don't need very high. That's a whole different ballgame. We all live in an age where vulnerabilities are being newly discovered every day, and even our core hardware we use everywhere all the time, freaking x86s, but any processor with caching is vulnerable to Spectre meltdown style attacks. And what do we do about it? And are we even now getting robbed blind by somebody in China, God knows what? I don't want to pick on anybody, but you just don't know. And there's a room for people to go think through how security works and why it works and when it fails and what does the crook do when he's looking to go rob somebody. There's a certain mindset involved there. So I think there's room for a lot of room for growth in a lot of different directions. I think there's new challenges for the new generation. To go right now. I think I'm being told to wrap it up right now, and I'm actually wrapping it up right now. So I guess we've got 2 minutes, so let's go around. What do you see as the new challenge that you would find useful for people to go look at, and do it in like 30 seconds so we can complete this job in 2 minutes here? Anyone can go first.
Okay, so I have a thought. I think as software has become a pretty mature discipline, we now have folks who need to interact with software that are not engineers. So of course, top of mind for me is data scientists. So how do we allow data scientists to do the equivalent of software engineering in their world? So I think that's kind of a big challenge is thinking about the second order effects.
Yeah, I'm going to second that and add to that. I think that software creation is going to become an increasingly more important medium of communication for people. And making it easier to understand software, making it easier to learn how to program, I think is a challenge that we need to rise up to.
I think pretty much my entire career I've been super frustrated by the fact that we spend 98% of our time doing things that seem unrelated to the task at hand. And shaving away at that, I think, is a noble goal and something to look into.
I think the challenge still remains how to get to a level of high correctness, to verify correctness without getting bogged down in detail. So if you want to go to correctness to the end game, you write code in Coq or Agda or Ethereum prover like that. But for most software, it's just incredibly hard to do and incredibly tedious. So the question is, how can we scale that up? That would be a big challenge for me.
Yeah, I said the exact same thing. How can we force the programmer up front to bear more of the intellectual burden of correct software, such that burden is not being borne by those in operations or production who are stuck debugging code?
Wow, thank you very much. I guess this will be the end of the panel, and I think everyone here deserves a wonderful round of applause.